Well, thank you all for coming to the LISP Part 2 talk. Once again, I will not introduce the man who needs no introduction, Dino.
Welcome all. So let's see, who wasn't here yesterday or last Wednesday? Everybody? Okay. So I'll just go through there's a few slides summary of what we talked about, and then we'll go into part 2, and then give you a preview for part 3, which is next Wednesday. Summary, we're going to start talking about the design goals for a mapping database, a couple of mapping database algorithms, and a service interface that we have to the mapping database, and then talk about how list sites talk to non-list sites. We call that interworking, not necessarily transition, but we call it interworking. And then some security and network tools that are available and issues, and a preview for next week. So the first thing we talked about last week was we want to control the core routing table growth, and we can do that with a level of indirection by not injecting EID prefixes into the underlying routing system. And by doing that, we could also provide low OpEx multi-homing and have the site control which way packets come in on each of their links. That was the fundamental multi-homing use case that LISP can provide. We're going to talk about some use cases next week, data center use cases, mobility use cases, but the one that was able to give us the best use case was scaling the routing tables and being able to do this multi-homing. These slides are just extracts from last week. You're not supposed to read them. It's just those are the general slides that are referring to those topics. What we did, or trying to do, is separate address space into endpoint IDs and routing locators. We call them EIDs and locators for short. And by creating a level of indirection, it allows us to avoid renumbering sites and allows the topology to roam. So you can roam topology because the site addressing could stay the same, and you just change the locators that access those EID prefixes. LISP is the protocol and the architecture to do that. LISP is a network-based protocol to achieve the separation in an incrementally deployable manner. You don't have to change site routers or core routers. We believe the sweet spot for LISP, but it's not limited to, is the CPE boxes. LISP uses packet encapsulation versus translation, like a NAT could do. A NAT is another example of an EID locator split. It just separates out a private address and a global address that's used. But LISP uses all global addresses. And packet encapsulation is what's used to be able to separate the addresses. And we map from an EID to a locator to be able to build the outer header. We described a unicast and multicast forwarding example when there was a map cache hit. So when there was a map cache hit, we used it, we encapsulate packets, we decapsulate on the other end. What we're going to show you today is that when we get a map cache miss, how we go get the map cache entry, and that's the mapping database system we'll spend probably half the talk on. We showed how site policy and core policy will be achieved independently, how the site can decide which way packets come in if it wants active multi-homing, active backup, or wants it to be per source or per destination. These policies can be achieved with pretty rudimentary tools. And then we talked about 3 mechanisms to deal with MTU handling. We don't believe it's a problem. You could add protocol machinery to solve it. And we talked about locator liveness algorithms. So the locators are always assumed to be up when you receive them in a map reply and a map cache entry, and then you find out when they go down or when they come up using the locator liveness algorithms that we talked about. And then we just talked about a little history of LISP and the open policy for it. We described that LISP its work started in the RRG, the Routing Research Group of the IRTF, and now it's an IETF working group. And we indicated that it's completely open with an emphasis of this is not a Cisco-only solution, this is an industry solution, and Cisco has no IPR. So let's move on to the talk. Anybody want to ask any questions or anything before I start? Okay, so the mapping database system. So what we talked about last week was machinery that's kind of been known, had been built before. It's not really, inventive or state of the art. We're just using existing mechanisms and just trying to define it in a very specific way and implement and learn about it. This part, the mapping database, is kind of the researchy or the new stuff, the new secret sauce, so to speak. And because we have to be able, when an ITR gets a packet, when an encapsulator gets a packet, it looks at the destination address, and it thinks it's an EID. So that's the key to the database lookup. And so it needs to get a locator set back so it knows where to encapsulate packets. And we want to require the destination site, to be authoritative and have secure control over how it replies. And the kicker is, think we needed to scale to 10 to the 10th entries. That's 10 billion. It's a pretty large database. Arguably, it's an NP complete problem, because if you can scale it to 100 million or a billion, arguably, 10 to the 10th is using the same set of algorithms. So we'll see, and you guys could be the judge if you think we can scale it to this size. The database needs to be dynamic, meaning that we need the locators to change, not real quickly, but at subscription times. If you reconnect to an ISP, if you maybe roam from one subnet to another, we need to update it. So it's very much like DNS with dynamic updates, maybe at the same granularity of time. We'll see as time goes on if we're going to have to be much faster than that. So that's built in day one. And obviously the algorithm has to be distributed, so we can load split map requests that go to different places. We need to use the entire network, all the boxes, bandwidth, CPUs that are available. And we don't want the database to be in one specific place or a set of places, or it could be DOS attacked. So by it being distributed, and we've seen this with BitTorrent applications, that if it's distributed, it's really hard to knock the service down because it's everywhere and you can't find it all the time. And so that's a good benefit, to stay ahead of the cat and dog game when it comes to security. So scaling internet databases. This is really fun. We need this EID to locator mapping service. And really, the internet today really only has two large databases. One's called BGP and one's called DNS. And they're pretty fundamentally different. And I'd argue that they're at different extremes. Where BGP pushes all the information everywhere. It's assumed that the information you need to route a packet is being told from everywhere to everywhere. So when you get a routing table hit, you can forward the packet on the next hop. But if you get a routing table miss, you should drop it because it's an unreachable or an unallocated address. Okay, so it assumes, the model defaults and assumes that everything's pushed hop by hop everywhere. DNS is completely different because it has to scale at a completely different level, where we will pull data only when we need it from servers. And it scales to probably 2 or 3 orders of magnitude more than what the BGP table is intended to scale. Now, what makes BGP scale is because the key or the information that's being passed around in this database isn't a power of 2, it has a power of 2 key. And it's called the IP address or IPv6 address. And because you can shorten the prefix, you can aggregate. So you can take 8 entries and advertise. If it's in the same power 2 block, you can advertise it into one prefix and lower the mask length by 3 bits. And because you're allowed to do that, as the information goes farther and farther away, the advertisement information goes farther and farther away, you can advertise more coarse information and be able to scale the routers that are farther away from the destination. Whereas the packet then moves towards the destination, each of the routers have more and more specific information to find the exact point where the destination is. So that's how we're able to scale to a certain extent if you can keep things in nice power of 2 boundaries. Sometimes that's challenging when you have backdoors and special policy cases and stuff. Now, DNS names they don't have power of 2 keys. They're just free-formed ASCII characters that are basically flat. So if you want to look up abc.com and xyz.com, basically there are 2 different entries that have to go into this database. So the only way to scale it is that you need to use a cache, and you only store what you're using on demand. And that's how DNS is able to scale. So you basically pull or push, and you need to choose your poison, because when you want to scale 10 to the 10th, it's not clear which is better. Okay? So we need to trade off state times rate. We know that the state's going to be 10 to the 10th. If we can keep the rate down, that factorial there will remain small. If they both have to be large numbers, we may have an NP complete problem. So we're trying to say that the state will be large and the route churn will be low, and that will maybe help us solve this problem. And we'll show you how we're going to go about it. Did I mention we have to scale it to order 10 to the 10th? It's really important. Okay, so mapping database algorithms. We have a few of them, and we documented most of them to tell you that they don't work and they don't scale enough. So when a new person comes along and says, why have you tried this? We say, it's in this class, go look at this. And then we have one in particular that has most promise. There are others that trade off things differently, and there's interesting new data structures like DHTs that could be used for this as well. But we'll go through each of these pretty briefly because we want to talk about the one that we're using now. So we have to trade off push versus pull and see what the benefit cost ratio is. So we have this one called NERD, and basically it's a full push. Let's make it look like BGP. Let's push all the data mappings everywhere. Let's push it from a few authoritative sources in some sort of trust chain, and they could be signers. So you know that the information is legitimate and coming from the right place. And then when you do map cache lookups in the encapsulator, you will never miss. It's either there, and when it's there, you encapsulate. When it's not, you should drop the packet on the floor. Okay, that makes the encapsulator pretty easy. You don't have to have any control plane machinery at that point. But that kind of violates the 10% routing table rule. That routing table rule is from Jeff Houston's data saying that a typical router today has 350,000 routes in a core routing table. But when you look at a 24-day packet trace of it, it only touches 10% of those destinations. So only 35,000 routes are being used out of 350,000. Is that a good use of memory? You might want to question that. So maybe on-demand caches, depending on where you are in the network, is a better way to do routing. And maybe with Lisp now, we should change the paradigm and not use push hop-by-hop protocols, but use a database. And when you need to go somewhere, you go request it, get the information you need, cache it, and then you use it. So that's kind of the paradigm shift that we're kind of going towards now with Lisp because it's a cache-based system. So do you really want to push all this stuff everywhere? Well, my Linksys router probably doesn't need a map cache entry. My Linksys router at my house probably doesn't need a map cache entry for Taiwan because I don't go there very often. Okay, I may go to China more often. So how do I decide to do that? Do I tailor it? What do you do? It's probably less is always better. And so it's probably a good idea not to have to push this around. We did some calculations on this and showed that only with a few gigabytes of memory you could probably store everything. And if you compress it, it doesn't take long to download it. The question is about dynamic updates. Dynamic updates would always be trickling in. You have to manage that. This is probably a non-starter, so we kind of put it in an obsolete sort of state. We have something called Emacs where we say, let's try pull, but let's do intelligent pull. Maybe we can take the EID and hash it to a multicast group. And then all the ETRs, the decapsulators, join that multicast group, and then I can send a map request when I need that information to the group. Of course, a bunch of people will get it which are not that destination EID, but the one who is will be the one who can send the map reply back giving me the information I need. Okay? So the first thing made a non-starter is, oh, what if I'm at my house and my EID range is the same as Google? I'm going to be getting a lot of map requests in because I'm joining the same multicast group as Google, so probably not a good idea. So we put that on the obsolete shelf. Cons had a lot of promise. We said, let's try to do a hybrid push-pull, and we will push EID prefixes, because pushing them with aggregatability of power of 2 addresses would be something we can do, and we can do that in a multi-level thing. You can't build a pure hierarchical thing because every ISP wants to be at the top. We live in a peer-to-peer mesh ISP type model, so what we want to do is build tier 1s, tier 2s, where all the big guys can be up there together doing link state, and the next level, the tier 2 guys can be doing link state. And so this was a way to push the EID prefixes on this thing, and then have the map request go up the hierarchy, come back, and have the map replies go back and forth. This was a completely brand new protocol, and we looked at it and we said, hey, we're using a lot of technology from the past, link state, path vector, these sorts of things. But one thing that's bad is that the map replies have to follow this hierarchy, and they may incur latency versus, just going straight. I have to go ask somebody where they live, but they say, before you ask me where you live, come over to my house and I'll tell you, okay? And so it's that catch-22 situation that we're in. So we came up with something called alt, which was similar to cons. Pushing EID prefixes is probably not a bad idea. And if we can do it on an alternate topology, we could probably make this scale really well. Today, when you connect into the internet, your address that you connect into is based on the topology. So your addressing depends on topology. If we can build a logical topology that depends on an allocation policy that the RIRs are going to give out, we can make this network map hierarchically in a power 2 chunks and really make the core store very few routes. So what we want to do is let's push these EID prefixes around using BGP, because we just need a routing protocol. Let's use BGP as a distance vector protocol. And let's have the BGP connections between these alt routers peer over GRE tunnels. Why GRE tunnels? Because we want this to be a logical topology. We don't want any physical association of these boxes with the underlying topology. We just want some peering model between VeriSign and GoDaddy, or Ripe and Aaron. And it doesn't matter where they are. And by the way, those BGP peering connections are going to stay up because there's a whole internet underneath you that's keeping the tunnels up. So the tunnels won't go down. The peerings will be stable, and we'll have very strong aggregation on this topology. You'll see in a minute. No changes to BGP whatsoever. These alt routers can be off-the-shelf Linux boxes. They can be Juniper routers. It doesn't matter. You're just taking a packet called a map request, and you're routing it on this logical topology. So we think alt has the most promise, and we've been looking at it quite a bit. We're in, I think, our 3rd or 4th rev of the internet draft, and we have it deployed. We'll talk about the deployed network next week. But we think it has a lot of promise, and it just dropped in so simple. It was one of the easiest technology introductions that we could have ever done. And we'll explain in more detail how this alt works. Okay. So basically, we're building. Go ahead, Stephen.
So I have a question.
Yes.
Address space. The DNS bigot in me says, why don't you just publish mappings in adder.arpa hierarchy or in the int hierarchy, and then you get all of the delegation of authority and all the mechanisms of DNS for free, and allow DNSSEC one day.
Yes, right. So the question is we already have a mapping database system. It's called DNS. Why can't we publish these prefixes in adder.arpa? And we have DNS updates, we have DNSSEC, and all these sorts of things. So we definitely started there day one saying, why don't we use DNS? And there's been many variations of that up to now. So the first gut knee-jerk reaction was, you don't want directly to depend on routing, and you don't want routing to depend on directory. So that's an interesting thing. If you needed to get to the directory, you'd have to use locator space, and you couldn't use list to get to it, or you have the catch-22. That was the first thing. Then the other thing is well, maybe we just use DNS the protocol, build a completely different set of hierarchy, and maybe we send our packets to something other than port 53 or whatever. And that certainly can be used as well. And there's the problem that we thought could occur, and there's a proposal now called LISP tree that the guys in Europe are doing, where they want to look at this hierarchy like we built with alt, but they want to see if these EID prefixes could be cached. Not the mappings, but the EID prefixes can be cached, and that you can lower latency. We're just not finding on the network that latency is a big problem. It really isn't that much of a problem. So we'd rather keep the center transport of the map request pristine, because if we have to pull out the middle and put in a DHT or the DNS idea that you have, Stephen, we certainly can do that. But we don't want to change the edges, the XTRs, the encapsulators and decapsulators. We want them to interface to this service interface, which we'll talk about in a minute, which are made up of map resolvers and map servers. So we have thought about it, but there's of course the IETF is going to say no, 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 and basically you could actually use DNS as a PKI as well, and you can put public and private shared keys in there, or keys in there, and have a hierarchy of trust, and that would work well as also. But the DNS specs say you're not supposed to use that as a general PKI. DNSSEC is supposed to use to secure DNS. Okay, so right. So this is kind of the model that we have so far, and we want to make it modular so we can pull out that red thing. Now, what's important to note is that the caching and the database map replies happen at the edges, and that's where it's authoritative. And the access to how you get map requests from this site to this site is serviced by these map resolvers and map servers, which we'll talk about in detail. And then these guys are just transporting those packets. The alt is basically a control plane infrastructure just to move map requests, a single packet type called a map request, which has an IP header on it. So a Juniper router can take a map request, which is an IP packet, off a GRE tunnel, look it up in a BGP rib, send it out another GRE tunnel to get it on its path towards the destination site who's authoritative for responding. That's the idea. Questions? So let's talk about the mapping service interface. Well, this was the example we had last time where we had S was talking to D and it wanted to inject a packet. Remember, throughout this presentation, green means EIDs and red means locator addresses. It'll be consistent throughout the presentation. So we see that the source is in 1001 out of the provider independent EID prefix that's been allocated to the site, the 1/8, and it's going to send a packet to 2002, which is D's address. Okay. So what we said last time was when S2 got the packet and it had a map cache entry, we would just encapsulate to the locator D1 or D2. What we're going to show you now is that the map cache lookup missed. And so what does it have to do? So what it does is it builds this control packet called a map request for 2002. So the destination address in the IP header says it's 2002. That's what I'm looking for. That's the database lookup key. And the source is actually the encapsulator or to-be encapsulator that his RLOC, his IP address is going to be in the source. So he has to send that somewhere. Let's just say for now, it gets to one of these two boxes that own 2/8, and then they're just going to send a map reply back to the requester, which is 11001, and it's coming from, say, D2. That's the map reply. That's the basic service interface. It looks very much like an ARP request and an ARP reply on a single subnet. That's kind of the idea. We'll talk about how it all happens in the center in a couple slides. What happens is when the map reply comes back, it has an EID prefix. It doesn't have 2002/32. It has the EID prefix for the entire site. So we have aggregatability. The map cache entries, when we said 10 to the 10th, we meant 10 to the 10th sites, not 10 to the 10th systems. So it's a lot of individual IP addressable systems. So this 2/8 is the entire site here, and we're saying that the two locators that you need to encapsulate to get to anybody in 2/8 is 12.0.0.2 and 13.0.0.2. We showed that last time. Once that map request, map reply exchange happens, you have the information you can encapsulate to.
One question. In the map reply, you should include information about 2.0.0.0/8, subnet mask information.
The question was, is that subnet mask information in there? It's 2/8. It's not subnet information. It's the entire power of 2 prefix that's used by that site. So out of the 2/8, there's a bunch of subnets here that have more specifics, /16, /24s that come out of the 2/8.
How does the S2 figure out the EID prefix to 0.0/8? The 8, where do you get?
It came back in the map reply.
Yes,
it came back in, yeah. The question is the map request was for a specific EID, 2002. How did the ITR know that 2/8, the /8 was the granularity or the coarseness? And that comes back in the map reply because these two guys know that they're 2/8. Scott?
Okay, so you can in fact do traffic engineering if you want to.
Absolutely. Yeah, Scott asked the question, do I have to send back /8s? And the answer is no, you can send more specifics back. And we refer to that idea as the Vince shower idea. Vince took a shower one day, had this great idea, and we refer to it ever since then as the Vince shower idea. This map reply could come back with a prefix with different priorities and weights. It can come back with a longer prefix. It should never come back with a shorter prefix. That's really bad, right? and we mitigate against that. But it could, be more specific. Because you may want to say that the EID prefix, this is the European region, and this is the US region, for instance. Sorry?
You can change the main one.
Yes, exactly. Other questions?
Question?
So essentially, for very busy load sites, you're talking about this demand-based cache population, but essentially for very busy sites like us, we'd have to, assuming the list was universal, our edge routers would have to have full tables with basically every mapping available, right?
Right.
For most, if 90% of what was lit
Right.
Right. So the idea, so we definitely reduce the routing table size in the core. But
Yes.
we basically were to push it back out to the edge.
Yeah, very good observation.
Okay. And also, isn't that sort of a vector for a pseudo denial of service attack if I just decide that I'm going to send you a mapping for every /32, right? If you ask me for something, I assume I can back some updates.
Let's hold the security questions to the end because I think I address all those. Okay, so let me re-ask the question so the people on the recording could hear. So the first question was.
Really just now for large sites that you have to carry the whole.
Yeah, that was a good observation. Is that large sites have to carry a large table? Will that table be larger than a BGP table? Not clear because you probably want people to come into you shortest entrance and give them shortest exit. So if Google wants to talk to 1 billion people, it's probably going to be 100 routers talking to 100 million each, or some power of 2 or order of magnitude difference. So I think that could be split up by the number of systems, and that will help. Let's see. Your other observation was, and I thought it was a good one, is that you're really moving the problem from large routing tables in the core to large routing tables on the edge. The answer is yes, that's true for a big site like Google, MSN, Yahoo, and that sort of thing. Not true probably for the edge sites, right? And we have mechanisms where maybe Google doesn't have to do the map request in the opposite direction. We could talk about that in a second. But yes, it's definitely trading it off, but it's putting the state in the places where they need it at the point in time and not putting it everywhere.
I think that's the key, though, because this complete set of EIDs isn't maintained across the edge ubiquitously, right? So it's dependent on the traffic pattern.
It's depending on the traffic pattern, absolutely.
I have questions about data probes in this context with regard to security as well.
Let me introduce what a data probe is first so everybody else can understand, and then you could ask that question at the end. Because this could turn into a security presentation, and I don't want that to be the case. Other questions?
Yeah, so I didn't understand how...
wait a second, J.I., go ahead.
You covered the exploration or validation of the map reply?
Yes. Yes.
You have a map, one word over there, right? But how does the map request reach the ETR?
I will talk about how the map request reaches the ETR in the next slide. J.I., you're on.
That's what I was trying to figure out,
okay.
How it reaches, how it knows how to probe it.
Okay, I'll tell you that in the next slide. One more question.
For many enterprises, they have not only just one /8 prefix, they may have many different address space. So when map reply back to the EIDs with all the IP address space they own, or just for one specific IP address.
So the question was, what if the destination site has multiple EID prefixes and a map request comes in for, say, one of them? Does the destination site return all the EID prefixes? The answer is kind of, and I'll explain why. In this case, if there was nothing, if this was the only ID prefix, you always return what it matches. And if the other ones weren't in the same power of 2 block, you do not return them. You can have overlapping prefixes, and in those cases, you have to sometimes return the overlapping prefix. In other words, this site can have a 2/8, but it also can have a 2/16. And in that case, you have to return the 2/16 because the locator set of the /16 could be different than the locator set of the /8. So we just put in the last specification that when they're nested prefixes, you return all of them. In the case of different, you do not return all of them. Just the one that you care about, right?
So why not just long prefix match?
Because if you go ahead, the question was why not just do longest prefix match? Is because if you do a map request on 2002 that matches the /8, and now you go ahead and have do another map request on another EID that matches the /16, you won't go map request to 16 because you got a map cache hit on the /8, and you'll use the locator set from the /8 and not the /16. You got to make sure that the course route doesn't screw you, is the bottom line, is the short answer. You can't have the course route match something when there's a more specific here, but not in the map cache. Let me continue because I'll answer most of your questions on how things work. Now, the big question is, and I'm surprised nobody asked, maybe you guys don't care, is what happens to the packet that invoked it? What do you do? Well, there's really three things you can do. You can drop the packet, just like ARP does in Neighbor Discovery. You can queue the packet. Well, talk to your hardware vendors. How much queuing are they going to do in the data plane? Or you can actually use the data packet, forward it, and use it as a map request. And that's what Ed was referring to as a data probe. Now, a data probe means it would follow the same path as a map request. But if we sent the data probe over the alt, then the alt's no longer just a control plane infrastructure. It would be used for some type of data packets. And then you do have a packet ordering problem because you'd be sending data probes on this alternate topology, and when you get the map request back, then you'll send it encapsulated, what happens there. So we have it in the spec because we think there's some data center applications where you don't need, like in an enterprise where you don't need a safe state, where you may want to send a data probe just on the default VRF and get and trigger something back. In those cases where you can't lose packets, like storage applications, maybe you want to use the data probe. But in the capital I internet case, we think that just drop packets, it's okay. Now, let's be clear about dropping packets here. It's only for the first time a first packet from any source on the left talks to any source on the right. After that, there's caching and you don't have this problem, okay?
I mean, it's the number of packets transmitted to the device and the amount of time that it takes to
The RTT time of the map reply, yep.
install it.
Yep, just like ARP,
So Noel,
just on a larger scale.
I saw Noel imply on the RRG mailing list that there was a solution, some sort of solution for the queuing version of this problem. And I don't
Well, he could be referring to various implementation techniques that could be used. Now, are they practical and cost effective to use? Another story. Okay, so let's keep going. So let's talk about this mapping service interface so we can show you how the map request actually gets to the destination where it needs to do. So this mapping service interface comes in kind of two forms. If you look at S2, it's this ITR. This ITR could have this GRE tunnel to an alt router. That's what the purple line is, okay? And when it wants to send this map request for 2002, it participates in BGP and knows the next hop. In this case, it's just one. Since it's single home to the alt infrastructure, that it just sends it that way, and then this router knows how to get it to its destination. The other interface is that S2 can actually encapsulate this map request and send it to a map resolver. And the map resolver is attached to the alt, knows how to get the packet to the destination. Okay? So let's talk about a little bit more of the mapping interface. Well, that's how the map request gets on there, but how do we get it to the site? So let's say we have this sort of scenario here where we have these three sites. Here's a 12/8, 11/8, and over there we have a 10/8, and those are those locators in green and red respectively. And let's say we have this alt network that's set up. This alt network can be run by service providers, interconnect providers, registries, governments, third parties, big hosting companies that start with the letter G, those sorts of places could do that. And what happens is, the first thing we say is this infrastructure also has these map servers that are attached to the alt as well as the map resolvers as we talked about as well. Now what happens, each site will register these mappings to a map service, and they do it securely with a SHA-1 authentication key that's shared. These two point-to-point, it's shared, no PKI needed. Okay, so they send map registers to these various map servers. What the map servers then do, what the map servers do is they inject those verified mappings into the BGP alt that runs here. And then at each level of this alt, we aggregate more and more and more as we get into the core. So basically, we built a topology with a distant vector protocol called BGP, so we can route a map request from there to this site through this topology. It's as simple as that.
Something like map servers or something like the HTML, it's like a classical IP server, something like that?
I have no idea. Okay. I don't know what it looks like. Everybody likes to describe solutions and reference something else, and I never like doing that because then you have to go down and say why they're different and where they're the same, and you get into something that turns out not to be a very fruitful conversation. Yes?
What is aggressively aggregated?
This topology is going to be built to map to the allocation. So if this guy has another power of 2 prefix that maps into here, he could register the same map server. But if it's not, say 2 years later, he needs more address space, he then will send a map register to the map server that's part of that delegation, that allocation delegation. And then it will then have all these /24s at this level that it can aggregate into a /21. And then this guy can take and aggregate into /19s going this way.
So it doesn't really have anything to do with the geographical distribution of that all.
Absolutely not. Yes, absolutely not. It's probably going to be registry based because the EID prefixes will come from registries in certain clumps. So if you get your prefixes out of RIPE, you're probably going to have to connect to map servers that are going to be supported in Europe at the /24 level. Now, that doesn't mean that a U.S. map server can't support a RIPE. It could, but it's all logical, right? And you would just have to send your map registers further on.
What's the difference between the map server and the map register?
What the question was, what's the difference between the map server and the map resolver? And I'll answer that as I keep going through the example. Okay. So the map server is the one who receives registration requests from the ETRs, so they can inject it into routing. Okay. And then the map request, what happens is these map resolvers sit there, and then when this guy up over here wants to talk to 10.0.0.1, which is down there, that the map resolver knows the next hop to get the map request to 10.1. And what will happen is each alt router just forwards this IP packet, along the path based on this distant vector protocol, and then the map request can actually make it to the authoritative guy. And then once he gets the map request, he can just reply back to the source directly. So the latency to get the map request goes on this logical. Hold on a second. The map request goes on this logical topology, and then once it gets to who's authoritative, the map reply goes back on the underlying network directly back. Did I answer your question? Yes. Okay. Go ahead, Jay.
For the VC ops, I can see you're a very handsome man, but I'd rather be looking at what you're pointing at. So you're pointing to stuff off in the screen to your right.
Gotcha.
Right. So if the
I apologize for that.
Yeah. Can they focus on the screen?
Gotcha. So let me review it real quickly. These ETRs here, you see my pointer? Or you want me to do it? We're going to get VC ops is at the table.
Yeah.
I thought there were separate VC ops.
So you're looking at the slides, right? Or are you looking at him?
I have on my right, I have the actual slides, but I'd also be likely looking at the screen, so when he's pointing at the screen, I know what he's pointing at.
How about, you see this pointer here floating around?
Oh, okay, that's perfect.
I'll use that.
Thanks.
So, quick review.
And I still get to see you.
Yes, no problem. I don't know if that's a feature or a bug, but... okay, so the ETRs basically are registering. They send a map register message to their configured map servers for their mappings here. And the map servers injected into this BGP structure. They each run an eBGP over these GRE tunnels. So let me go back to the animation so you can see it a little more clearly. And then let's just say when this ITR wants to be able to encapsulate a packet to somebody at this site, and it doesn't have a map cache entry, it will send a map request on 10.0.0.1. Now it sends it to its configured map resolver, and that gets it to the infrastructure system that knows how to route it. And then the map requests go hop by hop down here because this MS advertised 10/8 to the alt when the map register when the site registered, and it goes hop by hop throughout. And then you take shortest AS path. These can be, each of these alt boxes could be an AS in themselves, or you can have topology in here and run an IGP if you wanted to. If you're an ISP that likes doing those sorts of things, you can. But basically, BGP is being used as a distant vector protocol, so the map request can get to where you need to send real data packets. And when the map request gets to this point here, then it says, yes, I can give you this entry back. I know the source was from this guy, and I just send a map reply back to the guy directly to the map reply message is sent to the locator address, so it goes to on the shortest path on the underlying network. Better, J.I.? Okay, thanks.
So what's in the rib is the IDs.
Yes.
And the next hops are the map servers.
Okay, so the question was, good question, is what's in the rib in the alt routers are EIDs? The answer is yes for that. And the next hops are basically the IP addresses that are on the tunnel interfaces. Okay? So this guy just says the next hop to reach 10/8 is on this IP address, which is this tunnel interface. And then I just...
But ultimately, that gets you to a map server.
Yes, the map request gets to the registering map server, yes. And then this guy, Steven, oops, I'm doing the wrong thing. Okay, so this guy, when he gets the map request, knows who is registered to him, and then he sends map requests, he load splits them across all the locators that are at the site, which are the ETRs. So we do get, so if you register into multiple map servers, you can get the map request load going to multiple map servers, and then each map server then could load split the map request to all the ETRs that are at the site. So that's how we are able to make the load and scaling work a little bit better. Good, Stephen? Okay, go ahead, Ed.
In regard to the overall reply latency, there's not really a notion of geographical proximity here, and because of the fact that the first layer resolver doesn't cache anything, the request always goes back up through the ETR.
Right.
You could end up with a significant amount of latency if you have geographic.
The dominant latency is the speed of light and how far you have to go.
Yeah.
Right.
And if you're dropping packets during that period.
Right. So what we did as an experiment, and you'll see this next week, is my LISP router is at my house in San Jose, but my EID space is out of ripe space. And we wanted to see what it would cost for people to send me packets, but have to go all the way to Amsterdam to get my mappings, right? And we saw, it's the typical thing you'd expect, between 200 and 230 milliseconds was the latency. And yes, there are drop packets, but once it's cached, it's okay. Now, the map server spec does say we can do caching in the map resolver. It's not evident yet that it's going to be worth it. Because don't forget, everybody's inclination to say just cache because it'll do it better. But no, you don't want to cache this thing in a map resolver, because if that guy changes his mapping, he might know all the encapsulators and he can update them, but he doesn't know all the map resolvers in the world that are caching him. So the mapping update problem, a mapping update is defined to be, I'm going to change this locator set for this, or I'm going to change the priorities or weights for that. Use the mouse. Thank you. So you want to make sure that when these mapping updates change, that you know who to update, and you have to do it fast. For data center applications, we have to do it really fast. Go ahead, Stephen.
Okay, so your alt infrastructure is forwarding map requests based on longest prefix map.
On EID, yes.
EID. So what if that takes you to a map server that did not receive a map register request for a cutout?
It won't, because by definition it wouldn't have injected the BGP prefix.
So I can't inject 10/8 from the lower left and 10/16 from a different...
Absolutely not, because we're making the topology map to that allocation. We're not going to allow you to punch holes and be like the underlying BGP is today. See, since it's all logical and you can point these guys to any locator, and that these tunnels can be rehomed anywhere you want, we have flexibility without changing physical, geographical, or topological structure, underlying structure.
Okay, but then, in fact, you don't have the notion of delegating after the first delegation.
We do.
How? I get some space from Aaron.
Yes.
I give you half of it.
You are who? Google?
I'm your ISP.
You're my ISP. Sorry, ISPs don't get EID prefixes.
I'm the person who gave you half of his EID.
Then you're Aaron.
No, he's Aaron. He gave me some EID space.
Yes.
I like you so much, I give half of it to you.
Okay.
But you and I are forever entwined because
You made the dependency occur. If I want independence from you, the provider, I should go to him to get the prefixes. We want to decouple these dependencies. We want to decouple the dependency you have on the physical link with the address linkage that you have. It's very important. If we create new dependencies here, the decoupling won't work. Okay? Go ahead, Scott.
I'm not clear on earlier you mentioned the aggressive aggregation. How that policy, who's running that policy? How does it get applied, and how is that? So you're talking about the RIB and the EIDs, and you're going to enforce some kind of structure on these EIDs.
Yes. Where the boxes that are put up, and I have to keep a short answer, we're not going to get through the presentation. We could talk about it as long as you want afterwards. But the point is there'll be these different hierarchical levels, and there'll be different organizations that will manage boxes at each of these hierarchical levels. Those levels are predefined to carve out the aggregation boundaries of that aggregate space, okay? So if you want to be a tier 2, that means you're going to be at this level, at this alt level here, and you're going to be accepting /24s for map servers and aggregating them to /21s up. If you're at this level, and Google could be at both levels, maybe GoDaddy's here and VeriSign's there, it doesn't matter. But they're going to provide things at different levels, and they're going to try to create a service model. Now, these things could be monetized pretty easily because these are standalone PCs that can be put anywhere. We think that the interconnect providers or third parties will want to sell these things, just like DNS does, like GoDaddy does, that sort of thing. So this isn't changing the infrastructure. This is adding new boxes to provide a mapping service that can be monetized by various types of organizations. Service providers can get in this game because a lot of people think service providers are going to be out of the loop because you're just encapsulating and using the poor core service providers to just move bits and do nothing else. But the service providers could sell this service. They could package it with bandwidth. They could package it with other services and that sort of thing. Let me keep going, okay? Because I'm running out of time.
Quick question?
Yes.
Right, promise we're going to be quick. So if I'm a big organization and I decide to spin off or split off some part of me, right now I could just take the subnets or the more specifics that organization is holding and announce them as more specifics and let them be on their way if that's private address, if it's a portable address space.
The way that works in the LISP world is if you get those more specifics and you branch off and you go do something else, you will then register those prefixes, register them, not advertise them with a routing protocol, register to a map server that will take the /24s or more specifics so the aggregation could be maintained in the core. That's all.
Okay, thanks.
Okay, so let's get to interworking before we run out of time. We have about 15 minutes or so. I mean, I could keep going, but I don't know what the schedule is. So what's important about interworking is how does a packet exchange work between a non-LISP site and a LISP site? Again, pay attention to the coloring here because a non-LISP site has locator addresses, which means they're addresses that are routable on the internet, where the LISP sites have green addresses, which are EIDs, which are not routed underneath. So remember, when a packet goes from a non-LISP site to a LISP site, you got to always ask the question, how's it going to get there if there's not a route in the underlying network? So we're going to show how a packet's initiated from a non-LISP site to a LISP site and vice versa. Okay? We have two interworking mechanisms right now. A local uncoordinated solution where you don't need any infrastructure component to make this work, and we call it LISP NAT. We're probably not going to push it very much further. We've done some prototyping on it and we use it, but we think that really this new type of device in the network called Proxy ITRs and Proxy ETRs will be used, and we think service providers and hosting providers may want to do this, or interconnect providers, because this is a mechanism to attract traffic, and that's good for service providers. We coin these pitters and peters, but I will not burden you with that name. I'll call them Proxy ITRs and ETRs, which you can imagine what they do. So interworking with NAT, basically when a LISP site initiates a connection to a non-LISP site, it's a 1001 EID going to a 64001. Well, that packet obviously can get to the destination because 64 is underlying routing. So that just works. The packet gets there, no problem. Now the return packet cannot get there because 1001 is not on the underlying router. The EID is not in the routing tables, right? So what could we do? An EID address must be translated to a locator. So when you egress from a LISP site, that 1001 has to be translated into a routable address. And we're showing right here that it's being translated to 10001. So when this packet is egressing out through S1, S1 acts as a NAT, replaces 1001 with its locator, and sends the packet. That means the return packet could come back because it's being addressed to 10001, which means on ingress, it just maps it back. That's a kind of not necessarily a traditional NAT, but it's an address one-to-one based NAT that could be used. Let's talk about the cool stuff. Let's talk about building an infrastructure with Proxy ITRs. So let's say we have this non-LISP site on the left-hand side that wants to talk to a LISP site on the right-hand side. Notice that the addresses are in red and green, which means 128.1/16 is injected in the underlying routing tables because it's already there today or nobody talks to that site. We notice that 2.2/16, when this site on the right goes to LISP, it wants to withdraw that from underlying routing because it wants to be a good citizen and it wants the decoupling of addressing. Okay? So how will a packet get from S to D? Well, let's put these Proxy ITRs in the infrastructure. There's all kinds of service models and placements where you can put these. Let's don't talk about that right now. Let's just say we have these Proxy ITRs that will inject, I don't know if you can see in the middle, they're injecting 2/8. What they're doing is, and hang on every word I'm going to say, these Proxy ITRs are injecting a very coarse route for the EID range. You notice that all the sites will be in /16 or whatever their mask lengths are, it doesn't matter. But it's going to inject almost a default route, very coarse. So we're going to add a few routes so we can save hundreds of thousands of routes. That's the idea. There's a little bit of tax, okay? Now, why do we do that? It's because we need to attract packets from non-LISP sites. So what happens when S wants to send a packet from his locator to that EID, we know that the packet will go towards one of these Proxy ITRs. There's going to be an array of ITRs out there. Okay, so the packet will actually get to the Proxy ITR. The Proxy ITR will say, I'm going to look and see if 222 is in the mapping database. And if it's in the mapping database, I know it's a LISP site. If it's not in the mapping database, maybe it's routable underneath, and I'll just send the packet. So in this case, when it's in the mapping database, he's going to do the map request, map reply dance like he does. He's acting as an ITR at a site, but he's doing it for lots of sources. He's a proxy. And what he'll do is he'll find out what the locator set is for this particular destination and then encapsulate to the locator. The source locator is his locator in his infrastructure. And that's how the packet gets to D2. D2 decapsulates because he's 13002. Packet gets delivered. That's what Proxy ITRs do. Questions? Yes? Is that kind of a bottleneck? No. It's an Anycast service. You put 1,000 of them out there and they advertise 2/2, you go to the closest one. It's as simple as that.
What happens when one breaks?
If one breaks? What happens if a Proxy ITR breaks? Well, the 2/8 goes away and you go to the next closest 2/8. That's not what you meant?
No, that's not what I meant.
Oh, that's not what you meant. That was the, yes. Okay, what did you mean?
Well, I meant like a soft break, right? I mean, so it munges packets, it loses its little mind, obviously, right. You do something, but it's
yeah, I mean, shit happens, and I don't know. You call your vendor and you say, fix it ASAP, or I stop paying you for routers. I don't know. That's an implementation specific. I know those happen in real life. You're absolutely right, Stephen. You do not have to configure the Proxy ITRs on S. They just inject packets. See, those purple routers there are legacy routers. They don't know anything that's going on. They're old routers. They're your site today. All they're going to do is look at the destination address 2222 and inject it into the network, and they will have a route to it. It's just not going to go towards the destination. It's going to go through the Proxy ITR.
In the real world, there might be a 2/8 somewhere. Real IP address. Here, the IP address will be overlapped, right?
There's a possibility, yes, but usually it's going to be more specific, not less specific. If it's more specific, then it'll take the native path. And by the way, if it takes the native path, then you can reach the destination. That means this guy did not pull out his route. If this 2.2/16 gets injected and packets come this way natively, so be it. Then you just don't use LISP. At some point, you're going to pull the prefix and you're going to use LISP. And we've seen some people on our network say, I want to play with Lisp, but I don't want to withdraw all my prefixes. I only want this section to do Lisp. That's kind of like what Facebook's doing now. They say, I want this section to use Lisp. but not that section over there. So what they do is they keep advertising their more specifics in, and they try to have the PTR do the rest, right? Now, it's a little bit dangerous because we don't want more specifics to be injected by the Proxy ITRs, right? Was another question? Go ahead.
You just broke unicast RPF for the entire internet.
Oh, thank you for my next slide. I can move on. Okay, so my next slide, thank you. So let's talk about when a Lisp site initiates a connection to non-Lisp site, and then we're going to get into Steven's problem, right? And I'm going to solve his problem. So let's look and see here. We have this source site, and it's doing, huh? Yeah, right. So we have this site on the left-hand side. It's a Lisp site, and it's both doing, it has IPv4 and IPv6 EID prefixes, right? And, oops, let me go back one. Oh, can't. And let's say that this guy over here is a non-Lisp site and the guy on the bottom is a non-Lisp site. It turns out that I wanted to show you two examples at one time. So the above site's IPv4 only and the bottom is IPv6 only. Now, what we want to do is we have these proxy ETRs. Now, of course, the source site wants to be able to send a packet to non-Lisp sites, right? So what happens is that source is going to inject it to 128.111. What's going to happen is this guy is going to realize that I could route it underneath. It will get there, right? Because 128.111 is red. It's in the underlying routing tables. But if this provider A does not like 1001 because it's not in the routing tables, it's going to URPF fail and drop my packet. It's obviously not going to be an underlying routing, because if it's an underlying routing, we haven't saved the routing tables, and now we're putting the EID prefixes into the core, and we don't want to do that. So what we want to do is we want the ITR to encapsulate to this kind of default or array of proxy ETRs, which it's configured. So this guy knows that he wants to send packets to 64002 with his own locator, and he sends it to the proxy ETR. Of course, the proxy ETR decapsulates and then can forward the packet all the way. The reason we put this in place is because of the sun. The sun says we don't want RPF to fail there. So to hide, sorry, I'm walking out the screen. To hide this source address, all you got to do is encapsulate it in a locator that this service provider will allow you to do. I do this right now at my house. I can get from my house using IPv6 to IPv6google.com, and there's no IPv4 between me. That's the next example I'm going to show you. But I can also get to Daryl's house with IPv4, and I can load split my traffic on egress from Comcast and AT&T, no matter from the same host. And it doesn't matter what my IP address is, because that outer header is always a source address from the service provider that the packet is going out on. This is goodness. This is where the level of indirection gave you a benefit, even though there's cost with level of indirection as well.
How is this different from doing NAT on S1?
You can't do NAT easily when you're multi-homed. I'm going to keep that as a short answer.
Oh, okay. Okay, right.
Let's go to the next example.
Why can't you?
Let me go to the next example, and then ask away. So now, let's say S wants to send a packet to an IPv6 destination, but now this is an IPv6 Lisp site going to an IPv6 non-Lisp site. So what it's going to do, it's going to send it to 2001.128::1, and it's in routable space. Now, it could have the same sort of problem. If it injects it into provider B, it's going to drop it on the floor. Guess what? It won't inject it into provider B because provider B is IPv4 only service provider. So no matter what you do with IPv6, it ain't going to go anywhere. You could try to send it over the link. It's going to be dropped on the floor. So what S2 can say is, I want to send it to a proxy ETR, but I'm going to use an IPv4 locator proxy ITR and encapsulate an IPv6 packet in an IPv4 header. We can support all combinations, 4 and 4, 6 and 4, which is this, 6 and 6, and 4 and 6. All those 4 combinations are supported because they're just EIDs and locators. We don't care what address family they are. So what happens here is the proxy ETR gets the packet. He decapsulates it and says, there's this 2001.128::1, and my Peter is attached to this provider Y, which does support IPv6. I can open up an IPv6 TCP connection to Google today from my house, which is a Lisp IPv6 site, to Google, which is a non-Lisp IPv6 site. All because my DNS queries are on your whitelist and you return a quad A record to me. Thank you very much. Thanks, Eric, wherever he is. So proxy ETRs are used for these two basic features, and URPF has been a problem, Stephen. And we think we can, now what we can do with IPv6, and we'll talk about this more next week with the use cases, I'll admit it here on public TV, the router vendor screwed up. We had 15 years to put dual stack into the core, and we couldn't do it for whatever reason. All the OS vendors have put IPv6 in their stacks. We have all the end systems that could do IPv6. So we have all this IPv6 on the edges, and we can't get packets through the core. If you make those LISP sites and you use those IPv6 addresses as EIDs, you can use IPv4 as locators and jump over the IPv4 islands. Okay? So now IPv4 addresses will be used to address sites. IPv6 addresses, which are huge addresses, large address space, can be used to address every single particle on Earth. Okay? And you don't need a locator for every particle on Earth. You just need a locator to get you close to the particle. Okay? More about this next week. So this animation, go back. These stars mean that these two systems have an IPv6 TCP connection to each other, even though part of the path, the packet path, is IPv4. So let's look at the entire architecture one more time in one view. But so remember, we had the MRs and the MSs over here on this side, and we had the alt thing. Now what we're adding is the CPE routers, which are the legacy routers, the guys who are not non-LISP sites, and then the PITRs, Proxy ITRs or Proxy ETRs that are in the infrastructure. These boxes make up the entire LISP architecture and how you get access to the mapping database system. These Proxy ITRs and ETRs are attached to the alt because they must send map requests. Proxy ITRs and ETRs could send map requests to map resolvers too. It's just a proxy ITR is just an ITR for lots of places, but the functionality is no different than it being an ITR for a specific site. Same with proxy ETRs. We just leveraged the basic machinery you already had. We didn't have to make yet another device. Stephen.
So I'm going to ask my previous question in a different way now that you've introduced IPv6. I'm Hurricane Electric, and I have a tunnel service that basically, gives everyone, gives people who register for the tunnel service get IPv6 prefixes for me, and they get IPv6 connectivity no matter where they are. But enforcing that packets traverse this suboptimal topology that requires that the packets actually visit my network. If I could sweep all of that away and give everyone who had a tunnel, if I could say, you now have a LISP router, and you send you map register to me, Hurricane Electric.
Yes.
And I can now hand out map resolver answers.
Yes. Yes.
An IPv6 site could communicate, and a LISP-enabled IPv6 site could communicate with them directly.
Yes, that's correct.
So that the data plane data traffic doesn't actually have to go through Hurricane Electric.
Yes.
We have a line routing system.
Yes, so let me repeat all that for everybody on the call. So Hurricane Electric provides IPv6 service. I assume you meant Google when you said or you meant some service provider or something. I'll keep it that way. So what you're saying is you could deploy these proxy ETRs on that edge, and you can have customers IPv6 do IPv6 lists, but they're encapsulating v4 to you, so you can decapsulate and deliver the packets natively to IPv6 to the native IPv6 host. Yes.
Or if everyone who had a Hurricane Electric tunnel had a LISP router. Right.
Then they're just changing the type of tunnel. It's calling a LISP router where they have a dynamic locator. And by the way, that Hurricane Electric tunnel is a tunnel to one point. You can give people 4 locators, and they can load split the traffic across IPv4 locators to get to the infrastructure. Go ahead, Dave.
I think the important point Stephen was making was if you do this with LISP, it takes Hurricane out of the data plane.
Yes. Yes. Oh, yeah, yes. I didn't want to say that publicly, but you can. Okay. So Lisp security. This is I don't want to give Voltaire this credit for this. I want to give Dave Meyer this credit for this because he always says it whenever we try to build too complex infrastructure. He says the perfect is the enemy of the good. So Lisp security. These are the things we have in Lisp. Not too much, just enough, we think. ETRs use shared keys to register mappings to the mapping system. We use SHA-1. When you decide what your EID prefixes are because you call a registry, and then you connect to your service providers and find out what the locators are, you got this binding. Now you go buy service from a mapping service provider, and you say, I'm going to register this binding to you. The key's going to be 1, 2, 3, 4, 5. They configure it the same way on the other end. And they could also configure policy on that end, too, to decide which locators you accept with this verification key. So these EID prefixes are not injected into that alt BGP system unless it's verified by this manual process. This is good. Manual is good sometimes. The alt BGP is also secured with peering authentication, MD5, SHA-1 between neighbor peering things. But when we have local origin type certification and stuff and security with SBGP provides, we can actually use that too if you think the security needs to be put there. Don't know. The secure BGP stuff that's going on in the IETF. That's all. That's all I'm referring to there. ITRs do not accept unsolicited app replies. I hope this is addressing your comment, Ed. And the point here is that you must send a map request and you create a 64-bit nonce that you remember. The map reply must come back. We are using this basic concept called route returnability. If I send a packet to Scott and he replies back to me, the packet probably got to Scott. We are not going to address any man-in-the-middle attacks. Okay? So you can comment on that after the presentation. ITRs do not accept coarse or EID prefixes. That's really bad because right now if I think you're a /24 and you return a /8 to my map request, then you're saying I'm going to send packets to these locators for all these other sites. That's a redirection. Okay? So we don't do that because the map server can help you here, and you can use additional probing to find out what the real prefix is. As long as you send map requests on the alt, it is secured. The prefixes on there have been accepted and are secured. So the length of the mask lengths for those advertisements are real and validated. Map requests are rate limited. Okay. Negative map replies can source quench EID sources. So if there's a source sending too many map requests, the ITR can actually stop sending map requests for a particular source. And we have these negative map replies can give you these actions saying, I want you to natively forward a packet, I want you to drop a packet, I want you to send a map request. That's what and the map resolver can send negative map replies, and that is the mechanism to tell an ITR that a destination is a non-LISP site. Because once you find out something is a non-LISP site, you don't want to encapsulate because you don't know who to encapsulate to, and there's not going to be any ETR at the other end. So it tells you to forward natively underneath. Cache management suggestions are provided in the spec, and we could talk about that offline. That's the amount of security we have, no more, no less. So comments come later. I'm almost done. We could talk about security. Lisp and trace route. It's really important to find the entire path from source to destination. So the trace route gives you the path, the EID path from the source to the ITR, the path between the encapsulator and decapsulator, and the destination. It works really nice for IPv6 because the unreachable message or the time exceeded message contains the entire IP datagram. For IPv4, the original source is not in that datagram, so you have to do some fancy caching in the implementation to do that, but that's over beers too. We have something called LIG. It's equivalent to DIG, the domain internet groper, but it's the Lisp internet groper, and it's a way to fetch the database mapping entries. And we have both of the routers that we're shipping and prototyping now supported, and Dave wrote a public domain implementation that can run on Linux. And what this LIG does is basically LIG titanium dn list4.net is an EID. So it's ligging for this thing. It's sending the map request to that map resolver. And the map reply came back from one of the ETRs at the site. In fact, it's the only one. And here's the mapping database entry. Here's the prefix for it. Here's a locator. It's up. This is what the priority is. You can actually LIG yourself, and you can do it for IPv6. This is basically saying, am I registered to the mapping database? This is me LIGing at my house for my IPv6 EID, and what I get back is a map reply for myself saying I have 3 locators on Comcast, and this 6-to-4 tunnel is an IPv6 locator. So it shows you how it doesn't matter what the address type is. Okay? Okay, so that's it. Next week's going to be really exciting because we're going to now, so we've told you the what is LISP. We told you how is LISP, how it gets done. Next week, we're going to tell you why, and we're going to provide real business cases and real problems that are going to solve. And the key thing you need to remember is that we are creating a level of indirection, and we can solve so many problems with the level of indirection, and that we don't need to do hop-by-hop routing anymore. We don't need the core to join in on this sort of thing that we're doing on the edges. That's what the level of indirection gives you. Now, by doing that, we can move lots of things around by keeping EIDs fixed. People like keeping EIDs fixed because there's no management of that address space. You don't have to DHCP EID addresses to hosts anymore. The only thing that changes is the mapping database and the locators. And you don't have to inject more specific routes on the underlying network. So we're creating all these movement type features without bastardizing or unscaling the core, so to speak. So we're going to demonstrate, we're going to show you the dual stack LISP network. We have an alt network that we built. We're in the 3rd generation phase, and it's a dual stack, so it supports sending map requests for IPv4 and IPv6. Map replies can come back either way. We know when to send a map reply back. If I get an IPv6 map request over this infrastructure, I know if I should send back a v4 map reply or a v6 because I don't know if there's any IPv6 path. So if I send an IPv6 map reply back, it may not get there. So we have mechanisms where you can hop over these homogeneous address family type parts of the network. We'll show you some content and applications that are running on it, and we'll validating and testing some economic and service models. This 3rd generation network is trying to model these multiple service providers, mapping service providers, and how you would connect them. And we can show you the aggregation that you've been asking questions about next week, where the /24s get aggregated, the /21s, and how all that works. And we can see if there's a real service that people can monetize and sell for it. Go ahead, Scott.
So, yeah, I've been building a network for the better part of a decade, and I do deep peering and have trashed the entire idea of a hierarchical network. Could I start my own mapping service and have people subscribe to that and get the alt routes for me and not have to use hierarchical infrastructure at all?
So Scott says, I've been deep peering for a decade and the network's a mess. You mean deaggregating? Huh? Okay. You've been deaggregating is what you've been saying, right? And yes, somebody may have, and the routing tables are completely flat, right? There's a routing table entry for Scott White somewhere, which is, it shouldn't be Scott White, it should be Google, right? Or something like that. But yeah, yes, and then the follow-up question was, can I build my own mapping database and provide service to people? You certainly could, yes. And you don't even have to do it with an alt infrastructure. We're going to show next week one of the use cases that enterprises will want to use this. So say like a Wells Fargo or any other bank will want to be able to have all these branch offices. They have thousands of branch offices. Home Depot, Walmart, these retailers have thousands of offices. And they want people to pick up laptops, move from one site to the other, and they don't want them to have to DHCP or anything. They want the same IP address to be there wherever they move. And they want to build access lists based on the employee. So the EID is going to be static. This is a good thing. Static is good. It means it's going to be your network name for the rest of your life. This is IP number portability, just like cell phone number portability. And so, wait. And so what's going to happen is that they're going to build their own mapping database system as well. And we think it's just going to be made up of map resolvers and map servers. And since the ETRs register to all the map servers, they stay synchronized because of the registration mechanism. We don't have a cache synchronization problem among those servers up there. So the answer is yes, you could build a separate mapping service. Yes, go ahead.
The EID is still 32
bits. The question was, is the EID 32 bits? The IPv4 EID is 32 bits, and the IPv6 EID is 128 bits. Okay, so then the real meat is the use cases. And we showed up to now some multi-homing and remote branch use cases. I just gave you one. But we'll show you 4 data center use cases, which will be interesting. And we'll talk about LISP mobile node. And we're pretty excited about that. We are doing a public domain implementation on Android. And we're building a lightweight LISP implementation on Linux Android to show that we can take the concept of multi-homing a site to multi-homing a LISP mobile node. That's going to be really exciting. Dave's the leader of that project. Unfortunately, he's going to be at NANOG next week, but he'll be here in spirit for sure. Now that you can move a mobile node around and change its locators but keep its EID fixed, you can actually move an entire topology. You may have a topology of VLANs, routers, VMs, servers, all with an EID prefix, and you can actually move it to AT&T if they want to provide a cloud service, or Google. You want to move it to Google, and all that has to change is not the internal structure and addressing of that thing that you're moving, but the locators that reach it. So there's a lot of cloud computing use cases that you can use here as well. Questions? That's pretty much it for now, but throw the questions. Is this ordered in any way? Questions ordered in any way. The main spec, the main multicast spec, the map server spec, the alt spec, the interworking spec. The order is not in the way they were written. They're in the order that Dino typed them in, some logical order. The mobile node spec is there. It's still an individual submission, and so is the LIG spec. Oh, well, there's two types of packets in the internet. You know, one that's sent 99% of the time and the other that's sent 1% of the time. And you know which is which, right? So multicast would be a nice thing to talk about because we're starting to believe that trying to get, just like it's hard to get ubiquitous IPv6 underneath, it's going to be hard to get ubiquitous multicast underneath. Maybe unicast-based replication at the ITR is the best way to go, and you build a bandwidth demand service. So the sources could still multicast at the site, but when you want to leave the site, you can maybe unicast replicate. And we're thinking about, can we do that directly with LISP, or do you run this new protocol called AMT that encapsulates multicast and unicast, and then run LISP underneath that? So those are advanced research topics for the smart people in the world. So.
Are there drafts for security?
All the security stuff are embedded in each one of those. There's not a separate security draft.
Right.
But please look at it and hack if necessary.
Yes, Jay. Yeah, I'm right. You're right. You're right. Sorry. You're looking at the screen where I appear. So yes. I have been reading some of that, and I have quite a few security concerns. Where do I follow the normal IETF process of mailing the authors, or of the drafts, or do you want a different kind of process?
I would suggest you send comments to lisp@ietf.org, the working group list.
That's what I'm trying to avoid, getting involved in the IETF again.
Oh, that's a bug, not a feature.
Yes.
You're more than welcome to send it to the authors. Send it to the people on the front of this list, and it'll be fine. Is there a better one to send it to? Lispers@cisco.com? That's not a good one. Okay. So Lisp Ops is one. You know, you can send it to one of us or send it to me, Dino@cisco.com. I'll make sure I forward it.
Okay.
There's some public lists, but it sounds like you want to go a little bit private, and that's just fine. Thanks.
Thank you.
Yes, question. Can you share the slides so we can review later?
Oh, absolutely. I'll definitely share the slides. And I think all three parts are being recorded, so definitely. And if you want a subsequent presentation where we deep dive even further, we can definitely do that. And we could actually log in the routers and show you stuff if you're interested. We just want feedback. We want to learn more. We like bringing new blood into it because especially guys that have your type of experience, because there's new things that we may have not thought about, and it's nice to bring fresh. See, a lot of this stuff is pretty solid in our mind, and we can articulate it well. And if we can articulate it well, then you can ask us the things that we maybe didn't think about, or why did you make these trade-offs? So the feedback's always useful, so we definitely encourage it. Oops, sorry about that. Okay, thanks a lot. Oh, good.
Sorry, the cache validation was asked earlier. Negative map reply.
So the question was about cache invalidation. So we have TTLs in the, you asked the question. We have TTLs in the map replies. We're defaulting them to 24 hours now. When a negative map reply is being sent, we default that to 15 minutes. The negative map reply is not saying go delete a map cache entry. It's saying that a negative map reply is a reply that's saying, I have no locators for you. This is the action I want you to do if you match this prefix. Drop, natively forward, or send a map request. It's equivalent to NX domain. Yes, okay. I wasn't sure.
Are those sent on
They're never unsolicited. No, negative map replies. So what happens is I'll send a map request for the Google's IP address today for my home LISP router. The map resolver will look it up in the alt. The only thing that's in the alt routing table are EID prefixes. If it looks up that Google destination address in there and doesn't find it, it must not be a LISP site. So the map resolver sends a negative map reply back to me saying, in your map cache, put this prefix, and it's a coarse prefix, by the way, very coarse prefix, so that one map cache entry could hit most of the non-LISP sites. That tells me that when I match that entry to natively forward it and don't encapsulate. Okay. Now, and when an ITR is directly connected to the alt, it can look in the routing table directly. But when an ITR is connected to a map resolver, which is a datagram, it's a loose connection. You just send requests to it like a DNS query. It doesn't have all the data locally, so it has to ask the mapping system with a map request to see if it's a LISP site or not. Did I answer your question on invalidation, kind of?
I'll read that.
Okay. Okay. Thanks, guys.